The reactions that you're going to do today, they may seem challenging or hard, but like I said before, you're going to just match them. So you're going to make these note cards. You're going to make a note card for each of these types. There's a few kind of in between here. You're going to make a note card for each. Your homework is over there, and you're going to just try tonight to match 6 of them and solve 6 of them. Tomorrow, we're going to kind of blow through as many as possible. The more you practice, the better you get. The more you do without your note cards, the more confident you'll feel that you're going to ace the quiz and then the test. So tomorrow, we're just going to practice a lot. The activity series here, you don't get this on the AP exam. So you guys remember from Honors Chem, you got like a chart, and then things on the top replace things on the bottom. And if you had me, I related that to dating, right? We trade up. We don't date somebody and then choose someone that is worse than the person that we're dating, right? We always trade up. We always want someone better. So that's sort of how the activity series works. It says that elements that are less easily oxidized. So what does that mean? Oxidize means they give up or gain electrons. So something that's less easily oxidized means that it doesn't really want to give up its electrons. We'll oxidize elements that want to give up their electrons. So if they're oxidizing other elements, then what are they doing to themselves? They're being what? Reduced. So if something is reducing, then it means that it's oxidizing the other thing. So you can't take electrons from something unless something's giving them up, right? Electrons have to be exchanged. So one thing gives them up, one thing's accepting them. The substance that is willing to give them up is going to be the one that gets easily oxidized. So you could look at it in terms of a list, but you don't get this list on the AP exam. So you're just going to essentially assume that everything's occurring. You're not going to write NR, no reaction anymore. You're just going to go for it and say that these all are going to occur. So essentially here, gold all the way at the top is not easily oxidized. That's why we wear gold jewelry, platinum jewelry, silver jewelry, because it's not going to react readily. If your finger turns green, what metal do you think is on there? Copper, right? Because that does react, and it's lower on the activity series. So you'll see a green color from the oxidation of that. So this slide is just showing you, if you look at your activity series and you flip back, zinc goes to the +2 state, it gets oxidized. Copper in the +2 gets reduced, goes to the 0 state. That does happen. If you look here, zinc is here, copper's here. So copper gets reduced, zinc gets oxidized, just like I said to you, right? But this doesn't happen. The reverse of a redox reaction is not spontaneous, meaning it won't just happen on its own. Sort of like if I give you this reaction, where I put iron, solid, and I react it with oxygen and air, and I'm going to make iron oxide. This is rust, right? So if something rusts naturally, does it unrust? So that's not going to occur. So things that occur spontaneously in one direction are not going to occur spontaneously in the other direction. It says in this slide, zinc is more easily oxidized than iron. Go back to your activity series. Is that true? Zinc and iron. So zinc is more easily oxidized than iron. So that means if you have both of them there, which one's going to be involved in the reaction? The zinc. So this is actually just an interesting slide here that some industries will weld or just somehow react that so that the zinc and the iron are sticking together. They do this with other metals also. Even if this weren't just pure iron, it could be a metal alloy, and they'll put zinc on the outside of it. Zinc is kind of shiny. And so they do this especially for outdoor products because they're sitting out in the environment and in the air. And so they'd rather have zinc have a reaction than the iron having the reaction. If you get iron to react and you start making rust, did anybody have this happen in their house? Your sidewalk gets all rusty as it's coming off. It just looks nasty, right? But if you put the zinc on it and you coat it, then the zinc is called a sacrificial anode. And the word anode has to do with oxidation. We'll get to that in electrochemistry. But essentially, the zinc is sacrificing itself to protect the iron. Have you ever heard of a sacrificial lamb? That has connotations in like our world. We say someone's a sacrificial lamb or whatever that may be. It has biblical references, and it has references to you giving of yourself for the better of the team, for the better of the people involved, for the better of the situation. Well, zinc is the sacrificial anode because it's going to undergo a reaction and let the iron be because that's what needs to stay put for whatever product that the industry made. All right, so you guys will see this random question. So every time we get to these, I'm going to ask you to remember what you just learned and say, is it like that? Because you just have to clarify in your mind which reactions look like these. So this one, copper 2 nitrate solution is poured over solid zinc. Does that look like a precipitation reaction? That's the only thing you know right now is precipitation reactions and some very simple redox. That can't look like it. Why? Look at what I wrote for you for your note cards. What do you need to have? 2 aqueous solutions forming a solid. Is that 2 aqueous solutions? No. Clue 1 that that's not precipitation. What's your other clue? It has to be in what form? AB plus CD. Is there an AB plus a CD? Nope. So it's not precipitation. All right, so now we're going to go right to a redox reaction. This is a simple redox reaction. It's a solution with nitrate in it, so do I write nitrate? Do I write nitrate? Nope. Why? Because you don't include any spectator ions, and tell your group, what's your spectator ions? Tell your group. You have to use your voice to tell them. Go ahead, Lou, what are they? Well, because your group didn't tell each other. Go ahead, group. You don't know which ones are your spectator ions? You need new seats, group. Go ahead, tell Sweet Lou, he needs help there. Anything that's a group 1A or a nitrate doesn't get written if it's aqueous. Now, if I say it's solid, then you can write it. But an aqueous group 1A or a nitrate never gets written. And it says it's a solution and it's a nitrate, so we're not involving it. So I have 2 species here, 2 metals. I have copper 2 and I have zinc. So I'm going to ask you today repeatedly to use common sense, okay? These are your 2 choices. Copper 2 and solid zinc. Which one has to get reduced? What does reduced mean first? Gain electrons, meaning its oxidation number is going to go down, right? Okay, which one by default has to get reduced? Copper, why? What common sense do you know about zinc? What? Nope. Zinc's either an elemental form or a +2. Are you going to write a negative charge on any metal ever? You're not. So if you accidentally were like, I don't know which one to reduce, and you just went ahead and chose zinc to reduce it, you would get here and you'd be like, whoa, I don't know what negative charge to write. And then you would realize, well, zinc's not a negative charge, I must have done this wrong. So you will automatically know what gets oxidized and reduced based on your common knowledge of oxidation numbers off the periodic table. So we're going to start with Cu plus 2, and I'm going to turn that into what? So we're reducing that one, right? Cu solid. So later on in this lecture, I'll explain that you could also reduce this to Cu1 plus, but you don't. We're not going to do that right now. All right, so that goes to the solid state. So we know that that's getting reduced, which means that it has to gain electrons. How many electrons is it going to gain? 2. So plus 2, how do you know it's 2 electrons? Because this side has to equal 0 because this side is 0. Your left side has to equal your right side. Okay, and then our next piece here is the zinc. And we just said that we're going to oxidize that, and we all know that zinc's charge is a +2, which means that it gives up 2 electrons. So now we have to cancel our electrons. If they didn't cancel, then we would need to multiply by a number to make them cancel. But the electrons cancel with each other. And what's left, it doesn't matter what order you write it in, is zinc solid plus Cu plus 2 Aq yields Cu solid plus Zn plus 2 Aq. Good? That's a simple redox reaction. So there it is, printed nicely for you. All right, the next type of reaction is a halogen displacement. So halogens are which group on the periodic table? 17 or 7A, right? And look at them, either periodic table, look at them in the order that they appear going down the group. Fluorine, chlorine, bromine, iodine. Fluorine and chlorine are gases at room temperature. Bromine is a liquid at room temperature, and iodine is a solid. If you couldn't verbally say that out loud, what should you be doing right now? Writing them down, because you're going to have to write down their states, and you're not going to know what to write. So fluorine and chlorine are gases. Why? Because they have weak London dispersion forces. As bromine has more electrons, it's more polarizable. Its London dispersion forces are stronger, so at room temperature, it's a liquid. Iodine, again, increasing polarizability, so it becomes a solid. So fluorine being F2, is that going to be oxidized or reduced? Oxidized means oxidation number goes up. Reduced means oxidation number goes down. F2, it's a 0. Does it go up or down? Common sense. What's fluorine's charge? Have you ever written F plus? Nope. So if I give you F2, your only option is to reduce it, right? Which means then it's going to oxidize anything that's beneath it. So that's what this is saying to you. So the fluorine will oxidize the chlorine will oxidize the bromine will oxidize the iodine. That's how you're looking at this. This is the only time where you may have to predict that something has no reaction. Like if I gave you chlorine Cl2 gas trying to oxidize F minus, that's not going to happen. But otherwise, all redox reactions you're going to assume go to completion. This is the only one where I'm telling you a specific list that you have to follow. So this is really simple. Look at it. Chlorine gas is bubbled through an aqueous solution containing potassium bromide. All right, does this look like a precipitation reaction? No, right? You have a gas, you don't have two aqueous solutions becoming a solid. You have potassium in solution, and what do you know about potassium in a solution? It's a spectator ion, and so you're never going to write it, right? So then how could chlorine gas and bromide look like a solid, producing a solid? They don't. Okay, does this look like the other redox reaction that we just did with two metals? No. It looks like a redox reaction with two halides, which is why this is your halogen displacement reaction. So you're going to write what you have. I'm going to draw you a picture here. The first thing you have is a beaker with potassium bromide that broke apart into K plus and Br minus. So we have K plus floating around and Br minus floating around. Then I have a little tank of chlorine gas here, a little hose that gets bubbled in, and now I'm bubbling in Cl2 gas. All right, potassium's not involved. It's a spectator ion. So my only choices, again, are Cl2 and Br minus. Which one gets oxidized? Which one gets reduced? Common sense. Chlorine has to get reduced. Bromine has to get oxidized. I can't make this Br minus 2. You've never written that. That doesn't make sense. I can't make this a positive. That doesn't make sense. So you know that this one gets reduced. So go ahead and reduce it. What is it going to become? Cl minus, right? And what is this one going to become? Br. Halogens are always diatomic, right? So Br2. And I just told you bromine, at room temperature is what? A liquid. And this one became aqueous. This was your gas. This was aqueous. All right, now you need to balance your electrons. So this appears right now, if it went to a negative, that it gained 1 electron, correct? However, how many chlorine atoms do you have? And you only have 1 here, so you need to make it have 2 chlorine atoms, which means that this is going to be 2 electrons. You have to balance, whenever you're doing these, for atoms and charge. You have to do both. You can't just choose to balance for charge or balance for mass or atoms. All right, this one, same thing. I'm going to balance the bromide first. And then this must be that it lost 2 electrons. Remember that your left side has to equal your right side for atoms and for charge. So there's 2 bromine here, 2 bromine here, but check charge. 2 times -1 is -2. This is 0, and this is -2 also because electrons are negative, right? So you could always just check that your charges are correct by matching them. Like if I accidentally wrote 2 electrons over here, then my charge here would be -4, and that side would be 0. That wouldn't work. They have to match each other. All right, so now we cancel our electrons and go ahead and write out the final equation. So combine what's on your paper, cancel your electrons, and write your total equation out. Okay. The next one is a hydrogen displacement redox reaction. So these are all redox, except for the first lecture was precipitation. So in these, hydrogen gas, H2, gets displaced. In other words, it's your product. And it comes from water. So either you're going to memorize the reduction of water, or you're going to understand the chemistry and you're going to do the chemistry and then it'll make sense to you and you'll write this out every time. If you can't handle that, then you're just going to memorize this. So this is the reduction of water. The way that this works is that it's going to be a metal gets dropped in water. So if you see on the bottom it says alkali metals, which are your group 1A, calcium, strontium, and barium will displace hydrogen. So I drop this metal, any of these metals, into water and I'm going to do this reaction. That's kind of obvious, right? It's not a precipitation. It's not a redox reaction. It's not a halogen displacement. It's a metal in water. Every time you see metal in water, that's what you're going to do. You're going to do this. So it will either say, as simple as I just said, it gets dropped in water, or it'll be something like you have a piece of aluminum foil and they spill water on a sheet of aluminum foil. Isn't that metal in water? So you'll recognize this one. So if I'm telling you that water is getting reduced here, watch how you can you can solve for this without memorizing. So you have water, and you have to do something with this water. We have a -2 and a +1. It's the hydrogen that's going to get reduced here. Why am I not reducing oxygen? Yeah? It can't go under -2. I'm trying to make this common sense to you that you can figure it out. I'm not asking you to memorize all these varying things. I'm asking you to use common sense. I can't reduce the oxygen, so I have to reduce the hydrogen. If it's a +1, what state is it going to go to? 0, right? How do you make anything become a 0 state? Elemental form. So I'm going to make it become H2. Water is HOH, isn't it? If I cut out that hydrogen and I make H2, what's left? OH minus. Now I'm going to check for my electrons and I'm going to balance for mass as well. So if this went from a +2 to a 0, how many electrons did it have to gain? You just did this on your quiz. 1. I know it says 2, but I'm trying to help you realize why it's going to be 2 and not just memorize. Do you see that it's 1 + 1 to a 0 is 1? So this had to have gained 1 electron. It's not 1 electron because you have to balance for atoms. So you go and check. There's 2 hydrogens. There's 3 hydrogens. What do you do when you have an odd? You make it even by multiplying by 2. And that's 2, 2. So 4 hydrogens, 2 oxygens, 4 hydrogens, 2 oxygens. So now every water that you have, which there are 2 of them, is going to gain 1 electron each. So then this is why it's 2 electrons. Do you see how you don't need to memorize that? You're just going to come up with it by recognizing what that hydrogen has to be reduced, so it goes to H2, and then how many electrons there are. If you hate it, you memorize it. All right, so this is the reduction, and then by default, the metal is going to get oxidized. So try this problem. Sodium metal is placed in water. Easy to recognize, right? You make your note cards, you can mix and match them, and you can figure out which ones are which. A metal is placed in water. When you see a metal, that means it's a solid. You don't break it up, you just leave it. So I have Na, solid, and then I have water, liquid. So again, you have choices. Which one gets oxidized, which one gets reduced? Common sense. What's sodium going to do? It's going to have to get oxidized, right? You can't make its oxidation number go down to a negative. So if I'm going to oxidize this, this is going to become Na+. And if this is going to get reduced, we just discussed that the only way to reduce the hydrogen, right, we're not going to reduce oxygen because we can't make that lower than a -2. We reduce this by making it H2 gas. And then what's left is OH-. I balance this again. I have 2 electrons over here. I didn't memorize, I just did the chemistry. And then over here, I lost 1 electron. What do you do when your electrons don't match? How many electrons did the first equation lose? 1. How many did this one gain? What do I do to the first equation? Multiply the whole thing by 2. Okay? So now I'm going to have 2 Na solid going to 2 Na plus 2 electrons. My electrons will cancel, and then I'll combine what I have. So I have 2 Na solid plus 2 H2O liquid yields 2 Na plus AQ plus H2 gas plus 2 OH minus. So you check for the atoms and you check for charge, that you've done it correctly. What's the I'll let you guys write that out and then I'll ask you my question. So what's the charge on the left side, total? Because I said the charges have to equal each other. Left side has to equal the right side. What's the charge on the left side? What's the charge on sodium? 0. What's the charge on water? 0. So the left side is 0. Agreed? What's the charge on this? But there's 2 of them. So the total on this is +2. This is 0. What's this total? -2. So -2 plus 2 gives me a 0. So the left side 0, the right side 0. That's how you can check that you've done this correctly. And then you can count all your atoms back and forth and they will be equal, okay? So you can check your work. Oh, by the way, the hydrogen gas will catch on fire. That's just a side note here. When things show up, they're usually going to be on the side. So hydrogen gas can catch on fire. All right, next one is a disproportionation reaction. There's 2 of them. Big word, disproportionation. These are really simple. It's going to be a metal. Just one metal. There's nothing else reacting with it. It's a metal with itself. So the first type is disproportionation 1, is when you have 2 things going to, what did I write? Oh no, sorry, 1 thing going into 2 things. When I mean thing, I mean it's in its oxidation state. It has 3 different oxidation states. It's in its intermediate state, and it's going to go to the 2 other states. The other disproportionation is when you have the intermediate state going to the other 2. So you have 2 going to 1 or 1 going to 2 of the same element every single time. The only tricky part about this is that you have to know the 3 oxidation states. And you can't really guess them. You have to know them. So we're going to discuss how do you know the different oxidation numbers. So looking at the periodic table, you should be able to look at tin and lead and recognize what their charges are based on electron configurations. So tin is an S2P2 configuration. So is lead. So what are its charges? Tell your group. Plus, you lose electrons from the outermost energy level, right? So if it's S2 and then a lower D level and then a P2, you're going to lose how many? 2 and 4. You lose your S2 and then you lose your P2. 2 plus 2 is 4, right? So you're going to have a +2 +4 state for tin and lead. If you don't know them, if you can't say it out loud, you need to write these down. Because otherwise you're going to have no idea what to do with them later. These need to go on your note card. All right, let's take a guess at iron. Iron is an S2 3D6. Do you remember that rule I told you that atoms prefer to have half-filled orbitals instead of partially filled orbitals? Yes, Lou? What? I think you said it. plus 2 plus 3, plus 3 plus 2. 2, 3, 2, 3. Right? It loses its s, and then it loses 1 electron from its d to make a half-filled orbital. All right, the next ones I'm just going to tell you, and we're not going to talk about them. We're going to do iron, so you're going to start at iron. Everybody see iron? It's plus 2 plus 3. Cobalt, plus 2 plus 3. Nickel, plus 2 plus 3. And then we get to copper, and it's plus 1 plus 2. What's zinc? Just plus 2. It doesn't have a different oxidation state. You can't do a disproportionation with zinc. So it's iron, 2, 3, 2, 3, 2, 3, 1, 2. Get it? Starting at iron, it goes 2, 3, 2, 3, 2, 3, copper, 1, 2. The only ones that I'm going to ask you to make sure you know is tin, lead, iron, cobalt, nickel, copper. But you can do it. You know tin and lead. You know iron. I told you how to calculate iron and figure it out. And then it's 2, 3, 2, 3, 2, 3, 1, 2. Got it? Okay. So let's look at it. Your clue is always going to be it sits in a beaker. So you just leave something, a solution sitting in a beaker. The only thing it can do is go to 2 different oxidation states. 1 part gets reduced, 1 part gets oxidized. So if I have a solution of copper 1 chloride, the word solution clues you in that your chloride ion is the spectator ion, right? Because chloride can't do anything. It doesn't have 3 oxidation states. So you can't use chloride in this example. You can only use copper 1. So I have Cu plus 1, right? I'm going to reduce it and oxidize it. So first step, let's reduce it. What does it become? Cu solid, yep. Because that would give me the 0 state. So I just reduced it and I added an electron because it gained an electron. All right, then I have Cu1 again. I'm going to oxidize it. It becomes Cu plus 2. I lose 1 electron. Agreed? Because it's the only thing sitting in the beaker. So like some of it does this and then some of it does that. And how much it does, I don't really know. There's ways to figure that out, but we're not going to talk about that right now. So our 1 electron cancels. And then, look, there's 1 here and 1 here. So how many total does that give me? 2 Cu plus 1 goes to Cu solid plus Cu plus 2 Aq. And this was aqueous also. And then you check for mass and charge. This is 2 times plus 1, so this is a plus 2 on this side, 0 and a plus 2. So the left side is plus 2, the right side is plus 2. There's 2 copper atoms, and there's 2 copper atoms. So both the copper, 1, gets reduced and oxidized. Questions? Yeah?
How do you know it's aqueous?
Because it says solution. Yep. So clues are, if it says a metal, it's going to be a solid. Solution's always aqueous, and then gases will say they're gases. All right, disproportionation reaction 2. So look at what my note card says. And you guys can take pictures of those before you leave. If you want them to say exactly what mine say, then fine. If you don't, then you look at each of these slides and you figure out a way to make a note card for yourself. But I like to think of this as instead of 1 thing goes to 2 things, it's 2 things. What do I mean by things? Same element with 2 different oxidation states, right? Except that was long to write. So I wrote 2 things become 1 thing. So it's going to the intermediate form. So you have something with a 0, a plus, and a plus. You use the middle one, and you go to the 2 things. So we just did 1 thing goes to 2 things. Now we're going to go 2 things going to the intermediate state. So again, you have to know your oxidation numbers for the ones I just told you. So solid iron filings are added to a solution of iron 3 chloride. The solution tells you that the iron 3 chloride is in the aqueous phase. Am I going to do anything with chloride? Nope, because it doesn't have multiple oxidation states. So I have 2 things here. I have solid iron, Fe solid, and I have Fe plus 3. What's the middle one? Fe+2. Why? Because I told you to memorize it. So it's going to go to the +2 state. So you're going to do that first here. Fe goes to the +2 aqueous state. Is that oxidation or reduction? Oxidation. So I have to add 2 electrons here because this side has to equal 0 because this side is 0. And then I'm going to do it again. It's going to go to the same intermediate state. And so this goes from a +3 to a +2, so that must have gained 1 electron. This is the reduction. It's reduced because its oxidation number goes down. So the first equation has how many electrons? 2. The second one has how many? 1. What do I do to the second one? Multiply this whole thing by 2. So that's 2 electrons plus 2 Fe+3 AQ yields 2 Fe+2 AQ. So your electrons can cancel. And now you're going to combine everything you see. You're going to combine all your pieces here. And then combine those. So go ahead and combine them. I'm going to erase, and you guys will have the answer. So recognize the charge on each side is +6, right? The left side is +6, the right side is +6. You have a total of 3 iron atoms on the left and 3 atoms of iron on the right. Do you see how all these reactions are very different? It might be confusing. There's a lot I'm throwing at you, but once you recognize what you're looking at, you just do it. All right, combustion reactions. You guys know these from Honors Chem. Anything that's a hydrocarbon that burns in air is always going to produce what 2 things? CO2 and water. You're just going to do it. It's a redox reaction. I didn't tell you that ever before, but it is. So let's look at why it's a redox, but you don't really have to do anything. You just have to recognize a hydrocarbon is carbon with hydrogen. It could have oxygen in this also, right? When I say the word air, you write O2, and then you make it into carbon dioxide and water. Carbon is in a -4 state, +1, 0. It goes to a +4 state, -2, +1, -2. The key thing here is that carbon wants to be a +4. I don't know why. It just does. It's going to be a +4. So anytime carbon's involved and it's not in the oxidation state of +4, it will undergo a reaction to become a +4. And the only way to make it become a +4, well, one of the ways, is to make it CO2. So if I make it CO2, then it's a -2, -4, and then it becomes a +4 state. So if you want carbon to be a +4, you make it CO2. Got it? So for right now, if you get a hydrocarbon burning in air, that's simple. You just write CO2 and water. You look for that. On your quiz, you're gonna get a whole list of them, and then I let you choose. So I don't know what it is. I have to look at the numbers, but maybe I let you leave off 3. Look for the really easy ones. If I give you a hydrocarbon in air, you don't have to do really anything. You're just jotting down Honors Chem stuff. When you have a combustion of an element in air, then you have to try to figure out what to make it. So this is a non-metal burned in air and a metal burned in air. So if it's a non-metal plus O2, you're going to stick them. This is my own phrase. In other words, S plus O2, you make it become an SO2. So look at the oxidation numbers. 0, 0, -2 plus 4. Sulfur gets oxidized, oxygen gets reduced. You have to still make a redox reaction occur. You might be able to make this SO3. You just stick them. You stick the elements together. Got it? If it's a metal plus O2, you crisscross them. So calcium burned in air, calcium's a +2 charge, oxygen's a -2, I crisscross them, I get CaO. So I crisscross them. So if it's a non-metal, you stick them. If it's a metal, you crisscross them. Other redox reactions. All right, read this. Does this look like anything you've seen so far? The answer is not no. It might look like something you've seen before. I'm trying to be you. If I were taking this as a quiz, I might look at this and say it looks a little bit like something. What do you think it might look like? Maybe. Look at all the note cards in front of you. Not combustion because it's not air. It's not O2. What? Maybe a precipitation. That's the only thing I could possibly think that you might think it is. So I'm trying to be you and get confused like you might get confused, and then I want to point out why this can't be precipitation. All right, a few reasons. First thing is that it's not what? What does it have to have? Aqueous. It's not aqueous, right? Yeah, maybe you could form a precipitation reaction with gases, but at least one of them has to have an aqueous state. This doesn't have an aqueous state in here. And then hot iron 3 oxide, I realize that it doesn't say that it's a solid, but it doesn't say that it's a solution, and it's hot, so that kind of implies to you that it's a solid piece of something hot, right? And then there was something else I was going to say why this is not precipitation. I don't know. I'm kind of stuck with that. We have a visitor. Hello. All right, so if we have a redox reaction with things that we don't know how to handle, it's likely going to have carbon in it. And what are you going to do with carbon? You're going to make it a +4. So let's check to see what all of these are. So we're going to crisscross. Iron is a +3, oxygen's a -2. I crisscross, and I have Fe2O3. And then I add it to, and this was your solid, I add it to carbon monoxide gas. So let's check all the oxidation numbers on these. So write your oxidation numbers out. -2, -6. So this iron's a +3 because now it's a +6, right? Original oxidation numbers are +3, -2. Oxygen's a -2, carbon's a +2. All right, so that's your clue right there. Carbon doesn't want to be a +2, it wants to be a +4. So automatically, what do I write to make carbon a +4? CO2, okay? And now we have to figure out how to handle the iron. So here are your choices. We just made this a -2 and a +4. So carbon just got oxidized, right? So by default, this substance has to get reduced. It's the CO piece that became CO2. So if CO became CO2, then this is the other piece that's going to get reduced. Okay, is oxygen going to get reduced? Why? Because you can't make it lower than a -2. So what's going to get reduced? Iron. Reduce it. It's in a +3 state. Where do you want to make it go? Look at your charges. +2 or 0. You have a choice. It could do both. So if it becomes a 0, then it's Fe solid. What if it became an Fe +2? You're not just going to write Fe +2 because this isn't an aqueous thing floating around, right? It's not a solution. So how do you make it be a +2? What does it react with? The oxygen that's left with it, right? And you crisscross and you get or FeO. So this made it a +2 state, this made it a 0 state. It's up to you. You can make it go to either state, which is why earlier today when I was lecturing, you can make your copper +2 go to copper +1 or 0. It's up to you. So now you have to balance. Whichever one you chose, you have to balance for atoms and for charge. So you could write out your half reactions and check your electrons. You could write the atoms out and then check the overall charge. So if you wrote Fe solid, then here's your balancing. So 3CO, 3CO2, 2Fe. If you wrote FeO, then you're going to balance that separately. Okay, just one more. Acids. So this is hydrogen gas displacement again when you have an acid. So I could drop a metal in water and I can make hydrogen gas, right? Or I could drop a metal in acid. So if I say acid any words with acid in it right now, you're going to assume they're strong acids, which means that they get 100% dissociation, which means that they make H+. So for our purposes for this exam, because I'm not teaching you about acids and bases quite yet, I did a little bit but not in depth, if I write the word acid, you write H+. So I say acid, you say H+. Acid.
H+.
Great job, guys. So the reaction will look like this. Any acid makes H+. If it's sulfuric acid, that's H2SO4. How many H pluses are you going to get? 2 H pluses. So just be cautious. Sulfuric acid always dissociates to give you 2 H pluses. All right, so you'll have H+, and then your metal will be a solid because you drop a solid piece of metal in acid. And then the hydrogen obviously has to get reduced because you can't oxidize H+. You can't make that go up. It has to go down, so it becomes H2 gas. And then if that got reduced, then the metal has to get oxidized, so you go to the oxidation state. Pretty simple with that one. So try it. Write an ionic equation for the reaction that occurs when a solid piece of magnesium is placed in a solution of hydrochloric acid. So magnesium, solid plus what? H+, right? Because it's an acid. So we have magnesium, solid, and we have H+, aqueous. So you have to obviously oxidize this, and the only charge you know is magnesium +2, and this loses 2 electrons. And then this obviously has to get reduced into elemental form, which would be 0, hydrogen gas, and then this has to gain 1 electron. However, since I have 2, I have to balance for 2 atoms there, and I get 2 electrons here. The 2 electrons cancel. My final reaction is Mg solid plus 2H plus AQ yields H2 gas plus Mg plus 2 AQ. The end.